Welcome back to the channel. In the 13th day of the 100 D series of digital design and Verilog, today we are going to discuss about latches versus flip-flop. Before going to latches versus flip-flop, we'll go through what is combinational logic and sequential logic. In a combinational logic, the output depends only on the current input. There is no feedback loop or any storage mechanism. Time independence. As soon as the input change and after tiny propagation delay, the output will change. No memory, it does not know what the previous state was. What are the components it uses? It uses AND or NOT XOR. Common examples are adders, multipliers, multiplexers, encoders and decoders. So till now in our previous lectures, whatever example I have given you is all on combinational logic. Very rarely I have given sequential logic as example. In further lectures you will read in more detail about sequential logic. So what is sequential logic? Here the output is dependent on the current input as well as the previous state. So the time dependency here, the output is generated based on the clock. These circuits usually rely on clock signal to determine when the state should be updated. Memory, it uses storage elements to keep track of past information. Feedback loop, the output is often fed back to the input to influence the next result. We'll discuss in detail about this. Components built using flip-flops, latches and counters. Common examples where you can see them is registers, shift registers, RAM and microprocessors. In today's class, we'll be reading about these latches and flip-flops. See, before going to latches and flip-flop, we need to understand what is level sensitive triggering and edge triggering. So what happens is, this is your positive level and this is your negative level. So this is level triggered. In the same way, we have positive edge trigger and negative edge trigger. This is positive edge triggered. So the down arrow mark shows is negative edge trigger. So the top part is a level, that's a positive level, negative level, positive edge and negative edge. So first we're going to talk about latch. Latches are level sensitive. We'll see a basic example of an SR latch. An SR latch is the simplest sequential circuit. It has two inputs S and R. It changes the state as soon as the input changes, provided the enable is present is active. For as of now, for this example, let us not discuss about enable and just focus on the mechanism on how SR latch works. You have two inputs S and R, and the feedback mechanism is given from the output, that is the Q, to the input of the first XOR gate, and here the output of the second XOR gate is given as input to the first XOR gate. So when S is 0 and R is 0, the circuit will hold on to the previous state. So whatever was there in Q in the previous state, it will hold on to it. If you have S and R, that is S is 0 and R is 1, your output will be 0. That means it will hold on to 0. In the next state, it is 1 and 0, you will have 1. In 1 condition, regardless of this, you will have 0. That means you cannot get both 0, right? So we'll call it as indeterminate state. Now we have seen module SR latch in behavioral modeling. You have input wire S, R and wire enable, output reg Q. Before going, I'll also speak about what is enable. In general, enable is connected to a clock and it is given as a input to these XOR gates. So what happens is, when the enable is high, that means if enable is 1, this condition, all these conditions will run. If enable is 0, the SR latch will not work. It will not be active. It will be inactive. So always at whenever there is enable S or R based on the three inputs, if enable begin, it means if enable is equal to 1, then only you will begin this condition. That is what I mentioned here, right? If enable is 1, then only this SR latch will be active. Then you have case. Case is S and R. Based on the inputs S and R, you will give the output. So for 0, 1, it is Q will be 0, and for 1, 0, you will have 1, and for 1, 1, it is X. So it is invalid or forbidden state. default value, that is 0 0 state, is, you know, that it is equal to the previous state. It will latch on to the previous state, that is q. This is what I have mentioned. So as we saw, output q becomes 1 in when s1 is equal to 0 and s is equal to 0 and r equals 1. Output will q will become 0, that is reset. And when it is 0 0, it will hold on to the previous state, and 1 1, it is invalid or forbidden state. So here we get the race condition. You need to remember, in few of the interviews they'll ask what is the race condition. When both the outputs try to go to 0, leading to unpredictability. See, this is the case. This is called as race condition. Next we have different type of latches. In latches we have different types, that is SR latch, gated SR, D latch, JK latch. Here SR, it's a simple latch. Why is this called gated SR? Because you have an extra enable. It only changes state when enable is active. This is without the enable, and here no invalid state. Output follows input when enabled. Here in the last JK thing, it is toggles. It toggles when J is equal to 1, K equal to 1, prone to race condition. In the next video lecture, we'll discuss deep about latches. We'll learn about each of these latches. Then comes the another important part of sequential logic, that is SR flip-flops. Here the flip-flop is triggered by edge. When the clock pulse is on positive edge triggered or negative edge triggered, it will be active. An SR flip-flop, often called as a gated SR latch, when level triggered, or a master slave SR when edge triggered. So see, the same thing, the same diagram, whatever you saw in the latch, when it is level triggered, it will be called a latch, or when it is an edge trigger, it will become a flip-flop. Only looks at the S and R inputs during transition of clock pulse. Flip-flops are always modeled using always at positive edge clock to ensure the hardware synthesizer uses the actual flip-flop primitive. So you see here, as you have S and R, that is 0 and 0, and the output is previous state. 0 1, you will get 0. 1 0, you will get it as 1, and 1 1 is indeterminate state. So here again the same, whatever you had done for the latch, right, it is the very same. Only the thing that changes is here you will be giving always at positive edge of the clock. There we did not mention it. Here the only focus was on enable. If enable is 1, you will conduct the, that means the latch will be active. Here it is not like that. When the clock is at positive edge, then SR will be active. It means SR flip-flop will be active. Then we have different types of flip-flop. We have SR, D, JK and T. So here 1 1 is error, because when we spoke about this, we talked about indeterminate condition, right? So they have mentioned it as error. It is basic latching. Q follows D, data storage registers. JK is used for general purpose logic. T is used for binary counters. Again, on the day 13 and 14, 15, we'll talk about latches and flip-flops. This is your day 13th, right? So day 14th will be completely on latches. Day 15 will be flip-flops. Why do you use a latch instead of a flip-flop? Latches are generally faster and consume less power than flip-flop because they have fewer logic gates. They're often used in high-speed asynchronous systems or as small buffers in CPU design where timing is strictly controlled. Then you might arise with a question, when latches are only better, why do we require flip-flop? The short answer is predictability. Latches are transparent, which makes them a nightmare to synchronize in complex high-speed circuits. That means here for the latches, since it is a level triggered and it is asynchronous, it is difficult to give a proper timing discipline. So in that condition, we use flip-flops. There is also one controversial statement that most of them use, that is, latches are technically asynchronous devices, but they are often used in synchronous like ways. You need to understand what is this synchronous like. In a strictly synchronous system, nothing happens unless a clock edge says so. Latches do not follow that rule. Why? It is because of transparency. In a D latch, when the enable signal is high, the output Q follows the input D instantly. If D changes 10 times when the enable is high, Q will also change 10 times. It means here the latch is completely dependent on this enable signal, and there is no clock dependency. As I already said, it's completely dependent on the enable because the output can change at any time as long as the gate is open. The timing is dependent on the propagation delay of the gates, not a global tick. What it means to say is, when you are seeing the circuit, whatever your delay is present, no, it is because of the propagation delay of these XOR gates, not because of the clock. It is totally dependent on the propagation delay. After the propagation delay is arising, then the output can be seen. You will often hear people call a gated latch one with the enable pin as quasi synchronous. Now you might arise with a question. He is telling this the latch is asynchronous, but he's also telling it is synchronous. How is it? It is asynchronous because the input to output path is direct, transparent when enabled. But it is used synchronously because designers usually tie the enable pin to a clock signal to control when the latch is open. So when you are giving the enable pin to the SR latch or any of the latches, I will connect it to a clock signal. So that is how they become quasi synchronous. This is also a very important interview question. In the next video, we'll discuss on different types of latches and its operation. If you have any doubts, feel free to put it down in the comment section.